Hello, and welcome to this presentation, Understanding Spectrum Analyzer's Dynamic Range. In this short presentation, we'll explain the basic principles behind dynamic range and spurious free dynamic range in modern spectrum analyzers. This presentation assumes a basic knowledge of spectrum analyzer operation. If you're unfamiliar with spectrum analyzers, or if you'd like a brief review, you might want to watch the presentation Understanding Basic Spectrum Analyzer Operation before continuing with this presentation. The measurement of either very high or very low-level signals is fairly straightforward. Very high-level signals can be measured by attenuating them by a known amount. On the other hand, amplification can be used to more easily or more accurately measure very low-level signals. However, as we'll see in this presentation, the accurate measurement of both high and low-level signals at the same time can be very challenging. This is an important consideration in spectral analysis, since measuring very small signals in the presence of very large signals is a common measurement task. The term dynamic range is used to describe the difference between the highest and lowest amplitude signals, which can be accurately measured at the same time. The concept of dynamic range applies to many different devices, but in this presentation, we'll be focusing on dynamic range in spectrum analyzers. Dynamic range is normally expressed in decibels or dB, with higher values being more desirable. Most modern spectrum analyzers have a dynamic range of over 100 dB. Several factors influence the upper and lower limits of an analyzer's dynamic range. The low end is often largely determined by the analyzer's displayed average noise level, or DANL, and in some cases by phase noise. Maximum safe input power and compression often determine the upper limit. The presence of spurious products generated within the analyzer itself also play an important role. In the remainder of this presentation, we'll discuss each of these factors and how they contribute to an analyzer's dynamic range. The absolute lower limit of dynamic range is the analyzer's displayed average noise level, or DANL. This is the noise generated within the analyzer itself and is often referred to as the analyzer's noise floor. DANL limits dynamic range, since signals with amplitudes below this noise floor cannot be seen or measured. An analyzer's DANL is partly a function of the spectrum analyzer's hardware/architecture, often quantified in terms of the analyzer's noise figure, that is, the amount of internal noise that the analyzer adds to the input signal. But DANL is also a function of the analyzer's user-configurable settings. In particular, lowering either resolution bandwidth and/or input attenuation will decrease an analyzer's DANL, and thus usually improve dynamic range. Please see the separate presentations on noise figure and DANL if you'd like to learn more about these two topics. Phase noise sometimes also contributes to the lower limit of dynamic range. Phase noise is short-term variation in the frequency stability of a signal. This instability creates noise in the form of sidebands both above and below a carrier. In many cases, this phase noise is created by the mixing of an input signal with a noisy oscillator, and this is often called reciprocal mixing. Phase noise is usually greater the closer you are to the carrier. The noise power in these phase noise sidebands can also increase DANL, and thus the presence of phase noise can sometimes reduce an analyzer's dynamic range. Next, let's look at what limits the upper end of dynamic range. All spectrum analyzers have a specified maximum input power. In most modern analyzers, this is plus 30 dBm or 1 watt. This maximum safe input power is usually printed directly next to the input connector itself. If maximum input power is exceeded, the analyzer's front end can be permanently damaged or destroyed. So clearly this maximum input power represents the maximum upper limit of dynamic range. If signals with a power greater than this level need to be measured, external attenuators are a simple and reliable way to reduce input power to a safe level. But note that this attenuation can also push low amplitude signals beneath the noise floor. The internal active components used in spectrum analyzers, such as mixers and amplifiers, also limit the upper end of dynamic range. In an ideal active device with gain, the device input power is linearly scaled by the gain, so P out equals P in plus gain. However, If the input signal amplitude becomes large enough, a real device will no longer be able to produce this constant gain, and output power will no longer follow this linear relationship. This situation is called compression, and is usually quantified by the 1 dB compression point. This is the point at which the expected power and the actual output power differ by 1 dB. Compression limits how accurately we can measure high-amplitude signals. Even though the amplitude of this compressed signal can still be measured, recall that the definition of dynamic range is the range over which signals can be accurately measured, and this is why compression affects the upper limit of dynamic range. In addition to causing inaccurate amplitude measurements, compression can also create distortion or spurious products. These include both harmonics and intermodulation products, which are generated within the analyzer itself, and which are not present in the input signal. The frequencies of both harmonics and intermodulation products are usually related to the frequency and amplitude of the input signal, or signals, and thus can be predicted. In some cases, however, spurious signals may also be unrelated to input signal frequency, and may appear on the analyzer display even when no input signal is present. Generally speaking, spurious signals are difficult to filter out or otherwise work around, and thus the presence of spurious signals limits the range over which we can accurately or reliably measure signals. To quantify the effect of these spurious signals, we use something called Spurious Free Dynamic Range. Recall that we define dynamic range as the distance between the largest and smallest signals that can be measured accurately and simultaneously. Spurious free dynamic range is defined as a difference between the fundamental signal and the largest spurious signal. Unlike dynamic range, which is measured in dB, spurious free dynamic range in spectrum analyzers is reported in units of dBc, that is, dB relative to the power of the fundamental or carrier. This makes sense because the amplitude of the spurious products produced by an active device is a function of the amplitude of the fundamentals or input signal. The further a device is pushed into compression, the greater the amplitude of the spurious products it produces. Spurious free dynamic range is a more appropriate measurement than simple dynamic range, when dynamic range is primarily limited by strong spurious signals, rather than being limited by noise or compression. Let's end with a brief summary. Dynamic range in a spectrum analyzer is defined as the difference in dB between the highest and lowest amplitude signals that can be measured accurately and simultaneously. This is a common task in spectral analysis, and therefore dynamic range is an important figure of merit for spectrum analyzers. On the upper end, dynamic range is limited both by maximum safe input power as well as by compression, which reduces amplitude accuracy. On the lower end, dynamic range is limited by the analyzer's noise floor, or DANL, which represents the minimum signal amplitude that can be measured. Note, too, that the presence of phase noise may also increase DANL in some cases. A special case of dynamic range is spurious free dynamic range, which is the difference in amplitude between a fundamental signal, or a carrier, and the largest spurious signal. Spurious free dynamic range is measured in units of dBc, and is most often used when dynamic range is limited by the presence of a large spurious signal, rather than by noise or compression. This concludes our presentation, Understanding Spectrum Analyzers' Dynamic Range. If you'd like to learn more about dynamic range, spectrum analysis, or Rohde&Schwarz spectrum analyzers, please see the links in the video description. Thanks for watching.